Now, if you are given two vectors A and B, this is a vector A and this is a vector B. If you are given two vectors A and B, for example, then they have a unique resultant. In this case, for example, you can find the resultant with the help of the parallelogram law of vectors. This would be the resultant vector C, which is A plus B. The resultant of two given vectors would be a single vector C, uniquely obtained from the parallelogram law, or it could be obtained using the triangle law. Whatever is convenient at that point of time, you could use either the triangle law or the parallelogram law. Now, in case somebody gives you one vector C, in case somebody gives you one vector C and inquires of what two vectors is C the resultant. If somebody inquires of what two vectors is C the resultant, that means in this case A and B were given, C was unique. But I have a fresh scenario for you. I have a vector C given and I want to replace it by two vectors A and B. I have a vector C given and I want to replace it by two vectors A and B, right? How many ways can I do that? Infinite ways, because essentially then, if I have to replace C by two vectors A and B, then I want to be able to construct a parallelogram. I want to be able to construct a parallelogram whose diagonal is C. I want to be able to construct a parallelogram whose diagonal is C and whose sides are the vectors A and B. So, the number of parallelograms that I can construct out of the vector C would be the number of pairs A and B that I could find whose resultant is C. You know what I am saying? So, it's just about how many parallelograms could I construct whose diagonal is C. Infinite parallelogram. Because if this is the diagonal C, then I could, for example, construct a parallelogram like this. And the resultant of this and this is this, or I could construct a parallelogram whose diagonal is C, and in which case the vectors A and B are these vectors, right? Or I could construct a parallelogram like this, whose diagonal is C and whose vectors, whose sides are A and B. So there are infinite possibilities of constructing a parallelogram whose diagonal is C. So given the diagonal, the number of parallelograms are infinite. So the number of pairs of vectors A and B, the number of pairs of vectors A and B whose resultant is C is infinite. Each diagonal, each parallelogram constructed with C as a diagonal will offer a prospect of obtaining A and B. So with this parallelogram, I obtain a pair A and B whose resultant is C. With this parallelogram, I construct a diagonal. I construct a parallelogram whose diagonal is C. In which case, the two vectors whose resultant is C are A and B like this. In this case, A and B are like this, whose resultant is C. So for the same C, you have infinite pairs of A and B whose resultant is C. Is that okay? So now, given two vectors A and B, if I have to replace the vectors A and B by one single vector C, given two vectors A and B, if I have to replace those two vectors by one single vector C, then the process is called finding the equivalent. It's called finding the equivalent or the resultant, right? However, given C, given a vector C, the process of finding two vectors A and B whose resultant is C is called decomposing the vector or resolving the vector. decomposing or resolving the vector. Decomposing or resolving C. Replace C by two vectors A and B. Replace C by two vectors A and B whose resultant is C. And that can be done in infinite number of ways. Right. Now, so this process is called resolution of the vector C. This process is called resolution of the vector C. Now, the process of decomposing the vector C, there is the process of finding the parallelogram, could be nailed a bit. In the sense, I might stipulate conditions on how to find the parallelogram. I want to tell you that, well, decompose the vector C in a manner that its constituents A and B are perpendicular to each other. Decompose the vector C in a manner that its constituents A and B are orthogonal or perpendicular to each other. If this is a vector C, again, how many ways can I do that? This also would be infinite, because I can have something like this. This is a vector C, and it could be looked upon as the resultant of A and B, where A and B are mutually perpendicular. There are infinite number of ways of constructing a parallelogram whose sides are perpendicular to each other and whose diagonal is C. Yes or no? I could rotate this. A could be tilted a little bit, B could be tilted, and both could be perpendicular to each other, and I could construct yet another parallelogram whose diagonal is C. Is that okay? And now, if in addition I say that, well, if this is a vector C, I want you to decompose a vector C into two vectors perpendicular to each other. I want you to decompose a vector C into two vectors that are perpendicular to each other in a manner that one of the vectors is along this line, one of the vectors is along this line, the other vector is along this line. And these two lines are mutually perpendicular to each other. I say decompose C into two vectors, decompose C into two vectors such that one vector is along this, the other vector is along this. In which case, very clearly, there is only one way of constructing your parallelogram whose diagonal is C, and this would be the vector A, this would be the vector B, and the resultant of A and B would be C. Right? We say that C has been resolved into two components perpendicular to each other, A and B. We say that we have resolved C in two components perpendicular to each other, one in this direction, the other one in this direction. Is that okay? This kind of a decomposition of a vector in two mutually perpendicular directions, two non-mutually perpendicular directions, is called a rectangular resolution. It's called a rectangular resolution. It's called a rectangular resolution. That means now this was a certain direction, and one could have termed this as the x direction, for example. Right? Who stops us? The x direction, y directions, they are synthetic, they are man-made, they are not God sent. Any direction that you want, you can choose as the x direction. Any other direction that you want, you can choose as the y direction. Right? It will be based on some premise that will make life easy for a physical situation that you are dealing with. That's another story. But then, otherwise, no one limits you from choosing one direction as the x direction and some other direction as the y direction, the x-axis and the y-axis. Again, there is no limitation about the x and the y-axis being necessarily perpendicular to each other. We can have a system of coordinates in which the x and y axes are inclined at an angle omega with respect to each other. We say that this is a case of oblique axis. This is a case of oblique axis. Oblique axis, right? And this is a case of perpendicular or orthogonal axis. X and the y axis are perpendicular to each other in this case at 90 degrees, but in general they could be at an angle omega. But most of our deliberations would revolve around having our x and y directions being perpendicular to each other, right? So in this case, well, we can choose this as an x direction and a direction perpendicular to this as a y direction, constituting our xy coordinate system, Now, once you have synthesized your x and y axis, and then you are asked to do the following. You are asked to resolve C into two components, one A and one B, such that the resultant of A and B is C. Then there is only one way of doing it. A would be unique, B would be unique, right? This is called rectangular resolution. The vector C, vector A, this is the vector B. This is theta. Theta would have to be given. After all, once you are choosing the x-axis, then they would have to tell you, or rather you would have to decide how it's oriented with respect to C. So then this theta would be known to you then. Yes or no? Yes. So you can choose your theta. So choosing your x-axis is like choosing your theta, isn't it? ये अपने घर की खेती है, सोचो, ठीक है? So then C would be the resultant of this and this length, if this was mod C, this length is mod C cos theta. Do you realize that? Why mod C? This length is mod C, this length is mod C, yes or no? So this length by this length is cos theta. So this length must be mod C cos theta. So this length is mod C cos theta. How about it? Right? This mod C cos theta is called the component of the vector C along this direction. This mod C cos theta is called the component of the vector C, along this direction. Yes or no? Now, again, this length by this length is mod C. This length by this length is mod C. This length by this length mod C is sin theta. So this length must be mod C sin theta, right? But then this length is the same as this length. So this length is mod C sin theta. This is called the component of the vector C in this direction. Yes or no? So which means now, do you realize that this is the magnitude of the vector A? This is the magnitude of the vector B, and A and B are such that the resultant of A and B is C. Yes or no? So then we have a vector mod C cos theta. We have a vector whose magnitude is mod C cos theta, and along the x-axis we have a vector mod C sin theta along the y-axis. Clear? This I can refer to as some Cx, which is the x component of C, which is called the x component of C. This is called the x component of the vector C. And this is called the y component of the vector C. This is called the, and this is just a number. This is just a number. This is called the y component of the vector C. C, the vector C, is the vector A plus the vector B. The vector C is the vector A plus the vector B. Yes or no? But the vector A has magnitude Cx. The vector A has magnitude Cx. The vector B has magnitude Cy. Can I not say the following? The vector A must be Cx into a unit vector in this direction. If I cap was a unit vector along the x-axis, I cap, this is customary. If I cap is a unit vector in this direction, then a vector of magnitude Cx in this direction would be Cx into I cap. A vector of magnitude Cx in this direction would be Cx into I cap, yes or no? Right? So, if j cap was a unit vector in this direction, if j cap was a unit vector in this direction, then the vector B is of magnitude Cy. So, the vector B could be looked upon as Cy into a unit vector in this direction, yes or no? Right? So, then C could be looked upon as A, which is Cx into I cap plus Cy into j cap, where Cx is what? Mod C cos theta, Cy is mod C sin theta. Right? Cx is called the x component of the vector C, Cy is called the y component of the vector C. Cx and Cy are numbers. I and j are unit vectors along the x and the y directions. Yes or no? So you could write any vector C as its x component into a unit vector in that direction plus its y component into a unit vector in the y direction. I and j is traditionally referred to as unit vectors along the x and the y direction. Got me? This is a rectangular resolution of two vectors. No confusion, right? All of you understand everything. I know most of you would have seen all of this in my DVDs before and would have even read the text, but it's important that I ensure that you've understood everything and there are no gaps, because if your foundation on vectors is weak, then you will not understand anything beyond that. So even though it could be replication of things that you have already seen, I want to ensure that you've understood it all. And if you have questions now, make sure that you hurl them upon me. Yes. Really? Where did you learn your geometry from? In a rectangle, the diagonal will bisect the angle. This is a rectangle. Will this angle be equal to this angle in a rectangle? This only thing is this is 90 degrees. If this is 30 degrees, this will be 60 degrees. No. In a square it does, but not in a rectangle in general, right? Oh, never mind. It's okay. So, take it. If this is a vector A, this is a vector B, and this is a vector C. Now, I say in this case, he's saying I didn't quite get the hang of the order, right? So, let's put it in order. In this case, I claim that the vector A the vector B, and the vector C are in the same order. Now, what is meant by this? When I say they are in the same order, what is meant is, look, suppose there was a drunkard moving along A, right? Now, if there was no constraint, he would have perhaps continued to move along A. This is the direction of A. Now, someone wanted him to move along B. There was an escort with A. He wanted him to move along B. वो यहाँ जा रहा था, उसको जबरदस्त लात मारेगा यहाँ पे, इतना घूम जाएगा, ठीक है? He would have gone in this direction, जाके कुएं में पड़ जाता वो, ठीक है? मर जाता, लात मारा उसको, वो एंगल थीटा घुमा यहाँ से, सही, फिर सही रास्ते पे आ गया, ठीक है? And now, once he's on track, यहां पर जाता जाता जाता, एंड व्हाट सेंस, किस सेंस में लात मार के उसको यहां पे लाया बोलो तो? एंटी क्लॉकवाइज, राइट? दिस इज एंटी क्लॉकवाइज. सो फ्रॉम ए टू बी एंटी क्लॉकवाइज सेंस में लात मार के उसको ठीक किया, ठीक है? अब देखो, फिर ड्रंकर्ड यहां से यहां बिंदास जा रहा है, जबरदस्त विस्की पी लिया है, यहां पे जा रहा है, ठीक है? पर इसको जाना है गुरु यहां पर. फिर आदमी इसके साथ एक समझदार आदमी है, और लातों के भूत, राइट? फिर लात मारा बहुत जोर से, फिर लात मारा उसको, यहां पे ये घुमाया एंगल आ. अब ये बी टू सी में फिर किस सेंस में आया? एंटी क्लॉकवाइज सेंस में आया ना, राइट? फिर वापस सी तक आ गया, फिर कोई बात नहीं, ठीक है? वापस यहां से आया, सपोज अगर यहां जाता, इसको वापस इस ट्रैक पे लाने के लिए यहां जबरदस्त बीटा मारता इसको यहां पे, समझ गया? वापस इसको, तो इन दिस केस फ्रॉम ए टू बी टू सी इट्स ऑल एंटी क्लॉकवाइज, सो वी से दे आर इन द सेम ऑर्डर. समझ गया बात मेरा? यही फंडा. अब नाउ ऑपोजिट ऑर्डर, इसका मतलब समझ जाएगा कि दो क्लॉकवाइज और एक एंटी क्लॉकवाइज, सो एंटी क्लॉकवाइज वुड बी ऑपोजिट ऑर्डर टू द क्लॉक. दिस इज व्हाट इज मेंट बाय ऑर्डर, ठीक है? जब भी ऑर्डर का कंफ्यूजन हो, उस ड्रंकर्ड को याद करो और लात मारो उसको, समझ जाओगे ऑर्डर, ठीक है? सपने में मत करना कभी. Alright. Yeah, just in case you have questions from whatever you saw, I might address them first. If you have questions from whatever you might have seen in vectors. I'll explain. If this is a vector A, and then you say this is another vector B, right? Now to find the resultant of A and B in this case, what you can do is either go plain and simple, furnish the parallelogram and its diagonal, this would be the resultant, right? That's one thing. Now, the other thing that you could have done is, this was A and this was B, right? Kick B, right? I can move B parallel to itself without altering its effect. If I move B parallel to itself, well, then I could have moved B like this. I could have moved B to this position, yes or no? Which is the same as B being in this position. So I get rid of this. Now, two vectors taken in order. Now I've forced them in order. Two vectors taken in order, represented by two sides of a triangle. The third vector taken in the opposite order will represent the resultant of A and B. This C and this C would be the same. Right? Sure. No more disorders? Okay. Now, like I said, if there is a vector A, for example, then this vector is its component in the x direction. This vector is the component of A in the y direction. And I said if I cap is a unit vector in this direction, and if AX is the length of this, if AX is this length, then this vector is represented by AX I cap. This vector is said to be the y component of A. This length is referred to as AY. And if j cap be a unit vector in this direction, then this vector is written as AY j cap. Right? Now, the magnitude, so A is written as, the vector A is written as its x component AX into a unit vector in the I direction, x direction, plus AY j cap unit vector in the y direction. Clear? This length is mod A. This length is mod A. This length is AX. This length is AY. So if this length is AX, this length is the same as this length. This is AY. So then from Pythagoras theorem, can I not say that this square is this square plus this square? So this squared is mod A squared. That's going to be AX squared plus AY squared, AX squared plus AY squared. Yes or no? That's the magnitude of A. If a vector A is written as AX I cap plus AY j cap, then its magnitude is given by mod A squared is AX squared plus AY squared, where AX and AY are the x and the y components of A. So the magnitude of the vector A is going to be root AX squared plus AY squared. If a vector is given by AX I plus AY j, then the magnitude of A is given by root AX squared plus AY squared. So for example, if a vector A is given by 3i plus 4j, then magnitude of A would be root 3 squared plus 4 squared, which is 5. Clear? Now, this will give you the direction of the vector A. This will give you the direction of the vector A. Evidently then, if A is AX I cap plus AY j cap, then tan theta would be this length by this length. But this length is AY, this length is AX. So tan theta would be AY by AX. Tan theta would be AY by AX. So the direction of the vector A, given a vector A as AX I cap plus AY j cap, its magnitude is given by this, its direction theta is given by tan theta equal to AY by AX, etc. Right? This will give me the direction theta of the vector A represented in this manner. Clear? Now, no confusion so far, right? You understand everything that I have said. Let's say if there are two vectors, a vector A which is given by AX I cap plus AY j cap. Suppose this is one vector A. So the vector A has like an x component and has a y component, and this is the vector A, right? And let's say there is another vector B which is given as bx I cap plus by j cap. So the vector B has its x component of magnitude bx and his y component of magnitude by, right? That means B could be replaced by two vectors, one of magnitude bx along the x-axis, the other one of magnitude by along the y-axis. bx I cap by j cap. Yes or no? Now, let's say, if somebody tells you that the vector A is the same as vector B. Now, if somebody tells you that this vector is equal to this vector, if somebody tells you that this vector is equal to this vector, what it then means is, geometrically, if these two vectors are equal to each other, that means they are the same in magnitude and they are parallel to each other. If two vectors are equal, they must be the same in magnitude and they must have the same direction. That means they must be parallel to each other, right? Now, this is the x-axis for both, and this is the y-axis for both, right? Evidently, if this is parallel to this is the transversal. Do you realize that if this angle is theta, this angle will also be theta? Clear? Geometry. If this line is parallel to this line and this is a transversal, then these two angles must be equal to each other, corresponding angles. Corresponding angles, right? Now, if this length is mod A, then AX must be mod A cos theta, right? If this length is mod B, then BX must be this length, which is mod B cos theta, yes or no? BX is this length. Are you confused? If this B is the resultant of a vector of magnitude Bx along the x-axis and of magnitude By along the y-axis, Bx is the magnitude of B, isn't it? And the magnitude of B is this length. The magnitude of Bx is this length. Magnitude of Bx is this length. This component, this is a vector of magnitude Bx. But what is this length equal to? Mod B cos theta. This is mod B, this is mod B cos theta. Is it okay? So then Bx must be mod B cos theta. Clear? Hey, but if the vector A is the same as the vector B, then mod A must be equal to mod B. Mod A must be the same as mod B. If mod A is the same as mod B, because A and B are equal, they must be the same in magnitude as well as direction. So then AX must be equal to BX. Right? And similarly, what is this length equal to? Mod A sin theta. This length is mod A sin theta. So AY is mod A sin theta. Clear? And BY would be mod B sin theta. Okay. But again, mod A is the same as mod B. So AY must be equal to BY. Again, all this was not required. We could have deployed very simple geometry around this. We could have said, well, look at this right angle triangle and look at this right angle triangle, right? This angle is the same as this angle. This 90 degrees. These angles therefore must be equal, and these sides are equal in length because they are mod A and mod B. So these two triangles are congruent. This triangle will be congruent to this triangle, yes or no? If these two triangles are congruent, then their corresponding sides must be equal. So this side must be equal to this side. But this side is of length AX, this side is of length BX. So AX must be equal to BX. Similarly, this side is of length AY and this side is of length BY. So this side equal to this side would cause AY to be equal to BY. Yes or no? Which means if I have a vector A equal to this, a vector B equal to this, and if these two vectors are equal to each other, then I can claim that AX must be equal to BX and AY must be equal to BY. Yes or no? So if two vectors, in common parlance we say that if two vectors are equal to each other, their x and y components can be equated. Their x and y components could be equated, yes or no? So if I have a vector 2i plus 5j equal to li plus mj, then I can readily say that L must be 2 and M must be 5. If two vectors are equal to each other, I can equate their x and the y components. X and the y components. Sounds all right? Yeah, you had a question. Sorry, Yash. It got resolved? No components remain? Right.